more examples with the direct comparison test. Remember, we have to compare the given series to a series that we're familiar with, right? So just like with the other ones, we see this +1 or this +2, maybe a -1. Those are the things we want to kind of ignore and create a series based on what happens when you ignore this. So we're going to compare to the sum of 1 over the square root of n, right? Which is a p-series, which diverges by p-series because p is equal to 1/2, which is less than or equal to 1. Which means we can also look at the fact that 1 over the square root of n minus 1 has a smaller denominator than 1 over the square root of n. It's smaller by 1, so making a smaller denominator makes it a bigger fraction. So if the smaller one diverges, then the larger one must diverge as well. Therefore, the given series diverges by the direct comparison test. You might notice that we're starting with n equals 4 instead of n equals 1. We can't start with n, with n equals 1 because that isn't part of the domain. We could have started with n equals 2. Any finite value bigger than 1, we would have been fine. All right, cool. We're going to have to fudge a little bit on this one. Technically, the direct comparison test isn't perfect for this because the numerator is sometimes positive, sometimes negative. Think about the cosine of 1, cosine of 2, cosine of 3. These are almost random values as far as the cosine is concerned because there's no pi present, right? Cosine of 1 radian, 1 radian is in quadrant 1, so it'll be positive, but cosine of 2 radians is in quadrant 2, so it'll be negative. And we can't really use the direct comparison test when we have negative values, but we can also sandwich this between two different functions. Remember that the cosine of n is guaranteed to be less than or equal to 1, guaranteed to be greater than or equal to -1. So we could argue that there's a lower bound that exhibits the same behavior. So we'll go ahead and use the direct comparison test, even though it might not be 100% sufficient. We're going to compare to the series that does not have the messy cosine in it. We'll just change that to a 1, right? What does this do? Well, looks like a geometric series, right? With a common ratio, an r value of 1/2. So this must converge. So this converges by geometric series test because the absolute value of r, which is equal to 1/2, is less than 1. Okay, but again, ignoring the fact that we jump into negatives, we can see that the cosine of n over 2 to the n is always less than or possibly equal to 1 over 2 to the n. And since the bigger one converges, then the smaller one must also converge. Therefore, the given series of cosine of n over 2 to the n converges by the direct comparison test. Alrighty, so let's try this next one. Example F. If we go through the same process here and look at the -10 as being, the -10 as being something we don't really like, we're going to compare to the series 1 over n to the 4th, which, well, we know how that thing behaves. This looks like a p-series. P is equal to 4, which is greater than 1. So this series converges by p-series because p is equal to 4, which is greater than 1. Okay, so now we're going to compare the individual terms. Notice that 1 over n to the 4th minus 10 has a smaller denominator than 1 over n to the 4th. If it has a smaller denominator, then it is a bigger fraction. So we are talking about the thing that we know about converges, and the thing that we are asking about is bigger than the converging one. Well, that's not good. You can't really do that. The direct comparison test doesn't say that if the smaller one converges, then the larger one converges, right? There are lots of finite values bigger than the value that this thing converges to, but there are also infinite values that this thing might diverge to instead. So the direct comparison test may not work on this one. You might say, well, maybe instead of comparing it to 1 over n to the 4th, maybe we can compare it to 1 over n to the 3rd. And you might be able to make an argument for the direct comparison test there, but it's a lot harder to prove that 1 over n to the 3rd is smaller than 1 over n to the 4th minus 10. It is when you look at large enough n values, but it's probably not the best test. So we'll probably save this for the limit comparison test, which we'll look at in the next video. So anyway, let's move on and see if we can find a few more examples here. What's going on here? Yes, at one point I added an extra example in here. I don't really like the way it looks there, where I squeeze them all together. So maybe I'll slide this one over here, and if we have time, we'll do it. Here we go. But let's not clutter up the works here. So trying this one right here, what are we on? We're on blue now. I'm alternating back and forth. Clearly, we want to ignore that plus 2, compare to not having that annoying plus 2 in there. We look at that series and we say, oh, well, that series definitely converges by the geometric series test, right? Converges by geometric series test because r is equal to, well, the absolute value of r is equal to 1/3, which is less than 1. Therefore, the series converges by the geometric series test. Okay, but is this bigger than this? And so we have to ask that question. We have to actually state that inequality. And in this case, the bigger denominator makes a smaller fraction. So if the bigger one is converging, then the smaller one must converge as well. That is in the proper order. Therefore, the original series converges by the direct comparison test. All right, great. So I think we can do both of these. We'll see. I can squeeze them both in. You're looking at the same sort of, whoa, things are jumping around. Same sort of process on each of these. If we, again, ignore this 2, we don't like the extra constants here, so we're going to compare to the simpler series, 1 over the square root of n, which we already said diverges by p series, right? Because p is equal to 1/2, which is less than or equal to 1. So then we're going to compare this guy to this guy. And bigger denominator makes a smaller fraction. So we've got this divergent thing compared to the smaller thing. Uh-oh, the direct comparison test may not be best here either. Okay, so just because we can compare it and we see related series, as if we can't establish that the bigger one, if the bigger one diverges, then that's not good. And if the smaller one converges, that's not good. We need to have the opposite, so that, you know, if we have a smaller one that's divergent, then the bigger one must go off to infinity as well. And likewise with the convergent, we need to see that the bigger one is converging, therefore the smaller one must converge as well. And I think we're going to see a similar thing with this one, so I'm not going to go ahead and do this. Clearly, we have the sense that this behaves very similarly to this, so we have a feeling that it does diverge, but it's just that the direct comparison test doesn't really work for that. And same thing with this one. This is going to diverge, but not based on comparing this to 1 over n, because this thing is bigger than 1 over n. No, I'm sorry, this thing is smaller than 1 over n. So if it's smaller than something that's infinite, that's inconclusive, and we need to establish an opposite inequality if we're going to use the direct comparison test.